Hello everyone. In the first part of the lecture on costing in additive manufacturing, metal additive manufacturing specifically, we have seen a small introduction to what are the basic models or what is the basic structure of a cost in metal additive manufacturing. I will discuss certain models suggested by different contributors in this lecture, and I will also like to have a few examples in the forms of numericals. So, costing in metal additive manufacturing part 2, cost models are being discussed here. Then we have the cost advantage for additive manufacturing, we will see that. Then firm capabilities for additive manufacturing. The cost models defined or developed different thinkers, different researchers, but the one which is calculated by Hopkinson and Dickens and which is based upon calculating the average cost per part. I will try to demonstrate this model using an example here. Certain assumptions are there in this model. Number one, the system produces a single type of part for 1 year. Second is it utilizes maximum volumes. Number 3 is the machine operates 90% of the time. Now, analysis includes labor, material and machine costs specifically. Now, it gives a model in which the cost is the P in material into M plus P indirect into T. So, what are these? So, this is the price of the material, it is given here, price P material measured in euros per kilogram multiply the mass of the material. So, the cost is price of the material into the mass of the material plus price of the indirect cost rate, it is P indirect into the time taken by the build. So, this model is given here. Models which are designed or which they show or which they present are based upon certain criteria. For example, the break even point, the payback period or the total cost calculations, the rate of return or so. To understand the break even point, see break even point is when the money that is invested comes back, as I showed in the previous graph as well. This is additive manufacturing, the cost is constant throughout the units manufactured because the cost per part is specific here, right, it is per part and it is always fixed. However, for the conventional machining, because the cost of fixtures is there, as the number of components increase, we can have a better fixture, we can have a economical fixture, we can have a set of machines, we can have a special purpose machines, so many things could be gotten. So, the costs keep on decreasing per component here, but we have a break even point at a specific point where the cost of these two matches, right. So, this is a break even or the intersection point between the additive and conventional manufacturing. However, in general the break even point is what? For example, we have the total revenue or total cost, I would say here the left hand side in the ordinate, total cost or revenue. In the abscissa what we have is the number of units produced again, the volume or units produced. So, the fixed cost is always, this is the fixed cost, that is the investment cost, this is the fixed cost, I will call it fixed cost, and we have the variable cost over it. For each component the cost varies, this is the variable cost, right. So, this is the variable cost in general, and when the revenue, when the selling price is little higher than what is the variable cost is there, so it comes like this. So, here is our break even point, this becomes my break even point where the total invested cost or total number of the components which are sold have recovered my investment. So, this is my break even point for the number of components for the cost. So, this is in terms of the maybe say I would say rupees, and this is in terms of the number of units, that where do I get the break even point. Sometimes the variable cost is also not fixed. I would draw another graph here. Sometimes the variable cost is something like this, it goes something like this, then we change something, we add new printer and it goes like this. There itself also the revenue starts from here, let me say it would be something like this itself. So, here whenever we get the break even, whenever it is coming, we invested something new. So, this also sometimes do come when the profit is calculated and the loss is also there sometimes. So, this is the loss area. So, this is the general criteria to put any cost. So, before going to the detailed models for additive manufacturing, let us now first see a small example on the direct and indirect costs and try to see how do we calculate that. So, these are the direct costs. We can calculate the prime cost, factory cost, production cost, total cost and selling price based upon this data which is available for the year 1990 in the table. You can see the raw material inventory for 89 for purchase in 1990, then inventory for 90, different costs are given here. Then direct labor costs are given, then direct burden costs are given, factory expenses are given, administrative expenses are given. These are all discussed in the previous lecture. Let us try to see how do we calculate different kinds of the costs here. The first calculation that is to be taken to calculate the prime cost is the direct material to be used. Direct material used is the stock that we have in hand plus the raw material which is purchased minus the stock which was on hand in 1990, right, the recent one. So, that means this 25,000 plus 40,000 minus 15,000, all costs are in rupees. 25,000 plus 40,000 minus 15,000, which turns down to 50,000, right. So, this becomes my direct material. So, direct material here is rupees 50,000, rupees and rupees, plus direct labor plus direct engineering cost plus direct burden. So, direct labor, let us see in the table, direct labor cost here is 8,000, right. Then direct engineering cost is 6,000, direct burden cost is 1,000. Let us put these costs here, rupees 8,000 as our direct labor plus direct engineering cost which is rupees 6,000 plus direct burden which is rupees 1,000. So, 50 plus 8, 58 plus 6 is 64 plus 1 is 65. So, it is rupees 65,000. So, what is factory cost? It is the prime cost that we have gotten here as 65,000 plus the factory expenses. So, what are factory expenses? Let us see in the table. It is given the direct words factory expense as 9750, rupees 9750. So, 65 plus 9 is 74, 74,750. This is the factory cost. Next is the production cost, which is equal to factory cost, which is rupees 74,750 plus the administrative expenses, which is in the table. The administrative expenses are given as rupees 6,500. Just to have more clarity on what we discussed in the last lecture, I am just trying to solve this small example before you. So, this becomes rupees 81,250. Now, this production cost is rupees 81,250. This adding up the selling price, if it is given in the table, selling and distribution expense, it is given rupees 3,250 and markup rate this is 10%, number of unit produced is 650. Okay. So, the selling price, it is directly given as rupees 3,250, which means my total cost would be rupees 84,500. Now, selling price is total cost plus 10% markup price, that is 84,500 plus 10% of this, that is 0.10 into rupees 84,500, which is equal to rupees 84,500 plus 8450, which is equal to rupees 92950. Next, the total cost per unit is equal to total cost divided by the number of units. Number of units are given there, 650 units. Total cost is here. This is the total cost we have, rupees 84,500. 84,500 rupees. This is equal to rupees 130 per unit. Similarly, selling price per unit. Selling price per unit is very important because in the break even chart that you saw just here, these two lines are selling price per unit. This is the revenue line, this is the revenue line for the loss curve, this is for the continuous curve of the variable cost. I would say not curve but the line. So, this is selling price per unit is only plotted here starting from the origin. So, selling price per unit here would be the selling price which is 92,950 by the number of units, that is 650, which is equal to rupees 143 per unit, right. Now, considering the fixed cost which is not given here, this I will give as an assignment in the end. Consider the fixed cost as rupees 3 lakhs. Let me consider I have only taken a small printer. You just please calculate the break even point in the terms of units, in the terms of the rupees. So, this is a small assignment. Another example which I will not solve here, but that is just again a part of the assignment. Just see the terms here very carefully. We have like factory utilities, office utilities, direct expenses, sale commission, depreciation of the plant and machinery. Where would these costs fit well? Whether in the prime cost, whether in the overhead cost. For that, I have given here the material cost. Again, only you need to put the values here. The value for the material in 1988, then purchase in 89, minus the value of 89. Then prime cost is directly the material cost plus labor cost plus engineering cost direct expense. So, this is given there directly. Now, these are important things. Factory overheads. Factory overheads is the rent and taxes plus depreciation plus factory utilities plus plant manager salaries. So, this plant manager salary does not goes into the administrative expenses, it becomes only the factory expenses. So, that is why the factory cost here could be calculated as the total factory overheads plus this cost here, the prime cost, right. So, this is, I would just put here factory overhead plus prime cost, right. Now, the production cost would be the factory cost that we get from here, factory cost plus the administrative expenses, which are given here. Administrative expenses include the depreciations, the general administrative expenses, depreciation of office equipment only, office utilities, the office staff salary. So, this becomes here. The total cost obviously is the total production cost that we get here, we get the production cost. So, it is given a loss or profit something here. So, we have sales commission. So, this sales commission goes as loss. So, the production cost, this becomes my production cost minus sales commission. Then only you can calculate the sales profit and everything, sales income minus the total income. So please do this calculation by yourself. Now additive manufacturing cost advantage. Significant cost studies look at material and equipment costs, but inventory and supply chain expenses may hide many benefits. An automotive assembly dollar returns in 10.9 days, it is an inventory for 7.9 days. It is in production for 19.8 hours, in downtime for 20.6 hours. See, out of the 10 days, it is in inventory for this time. Out of the production hours, the downtime itself is bigger. Inventory takes another 1.3 days, 51, only 8% of the time is spent producing. Inventory and waiting account for 92% of the car assembly time according to the lean manufacturing. So additive manufacturing cost advantage, what does it say? The car assembly, engine parts, steering, suspension, powertrain, body and others are made separately and have different inventories. These parts are also shipped. Average transport equipment shipping is 801 miles. So this is a scenario which is given that US moves 45.3 billion ton miles of equipment annually. Because of additive manufacturing, it can produce a full assembly in one build. It decreases the transportation and inventory expenses, impacting the supply chain. So this was what was discussed in the yield structure costs as well. The transportation cost could be controlled or could be taken care of. But this is not a very practical example. The whole component, the whole car cannot be manufactured at this point of time using the metal additive printers. But still, to talk about the amount of the transportation cost, amount of the lead time, amount of the inventory costs which are all involved, how could it be compared? So for this model, that also talk about the extraction of the raw material and talks or takes it to the sale of the product. So this is the model where the cost for additive manufacturing is divided into the major three components here. Number one is MI, number two is P, number three is FGI. What is MI here? MI is the cost of material inventory for the R and M for additive manufacturing. What is RMN? That is for refining that new material and for manufacturing that material, right? Now, cost of material inventory for refining material plus cost of material inventory for manufacturing the material is the first component. Now, this is the cost including the administrative expenses for the material extraction. E is for extraction, R is for refining and M is for manufacturing. The second component gives us the factory cost. Factory cost means the administrative expenses are also included and the processing cost is also included here. Next becomes the cost of the finished goods. Again, for the finished goods, the cost of inventory for E, R and M for additive manufacturing is given. E is extraction, again R is the refining and M is manufacturing. Finished good inventory for extraction, finished good inventory for refining and finished good inventory for the manufacturing. So this is the model which is given for additive manufacturing. In the traditional model, what we saw previously as well, it is also put here into the four components, that is material inventory, then the production cost, then we have the finished good inventory and then we have the trading cost as well. Because in the finished good, in the traditional manufacturing, the traditional processes are also here, which include some more cost, for example in transportation, for example in retailing, for example in wholesale. These costs are additional here. This component is additional. So the first component is material inventory cost for refining, R is for refining. Number 2, I is for the intermediate goods. Number 3, A is for the assembly, right? Now, production for the extraction for the traditional manufacturing, for the refining, for the traditional manufacturing, for the inventory in the traditional manufacturing and assembly in the traditional manufacturing. This is second component. First, second. Third comes the finished good inventory for the extraction, the cost in extraction for the finished good inventory. The finished good inventory cost included for the refining, finished good inventory cost for the intermediate goods, finished good inventory cost for the assembly. In addition to it, we have the wholesalers, which includes the cost of the trade, wholesale trade, the cost of the retail trade and cost of the transportation, which includes the transportation throughout the supply chain. It is given here, transportation cost throughout the supply chain for a traditional manufactured products. Now, these two models gives an understanding of the costing between the additive manufacturing and for the traditional manufacturing. You can see in additive manufacturing, the wholesaling, the retailing law is all absent because we do not transport those things here, and the intermediate goods is also absent. Intermediate means in additive manufacturing we directly convert the raw material to the product. Raw material is the filament, it could be powder or any other forms that we get into, then that converts it directly into the final good. But in traditional manufacturing, the raw material goes through certain processes. For example, first we might have to get billets. Billets are metal formed to get into specific shapes. For example, hexagonal shapes, bars are taken then. Then those bars are then processed. That becomes the next level of the materials. So the cost of the intermediate goods is an additional part here. I will mark it here. And the wholesale trading, retail trading, and transportation. These are also additional. Next is additive manufacturing cost, that is production for additive manufacturing, is better understood than other manufacturing costs. Most cost studies evaluate a single part or component. However, additive manufacturing may save money on the complete product. Traditional manufacturing needs several intermediate goods, as I just talked, that must be transported, that must be assembled, that must be kept in between into inventory into the different boxes. Whereas additive manufacturing can achieve the same final result with a fewer components which are built simultaneously on the same area. So, if suppose we consider a future possibility for an entire maybe a jet engine housing to be made in one build using additive manufacturing versus having parts being shipped from different parts of the country, having goods inventory, administrative staff, having transportation infrastructure and everything. So, cradle to grave examination is needed for all these for the life cycle, but additive manufacturing might help if in future if this comes to a single production unit here to produce everything at one place. However, many of these benefits aren't included in the cost model. For these benefits, a cradle to grave examination is needed, which I just said. Time is a crucial factor in all goods and services production, as many operations management talks show. So, land, labor, human capital, entrepreneurship, time are the basic production components. Human capital and entrepreneurship are vital in additive manufacturing, but this is not a focus of this lecture at this point of time. So, labor hour or labor hour per hour, if I try to see that, for example, if the time is going on, if the time is here, and if I try to say labor cost per hour, so it would be keep on reducing as and when the time keeps on going, because we keep on instilling the labor hours per hour more and more into the system. So, this graph represents here that suppose if I put 50 workers, they can do the work in this time of time, and if I have only one worker or 5 workers, they will take this time, longer time. For example, to construct a house in a way, 50 workers would do it in a maybe 5 days, or 5 workers would do it in 100 days or so. So, this is what this analogy is trying to tell. Now, in this also, if we try to say the use of the resources, the use of the resources would be very heavy. If I say the resources use would be something like this. This is the use of. As and when time keeps on going, the resources, the natural resources that we are using, or let me say for example land only, because we are mentioning land, labor, human capital here, those would also be keep on increasing. The more land, the more time, the more material, everything would be taken more. So here everything is taken at heavy, but in lesser number of time. So more is used, but in the lesser number of time. As the time increases, the number of resources would be reducing here. So this, a machine reduces production time and labor, but uses more energy. This is one of the maybe examples for that. So here triangular plane shows different combinations of the land, labor and time. Then moving along this plane changes the resource use. That is, for example, if I move from here to here in this direction, this would become smaller, right? Which means we are moving towards the closer time, and profit can be maximized by changing and reducing the manufacturing resources. So we can have in the shorter time with the lesser labor and with using the lesser resources, the production ready. So this is advantage, or this is a total advantage of the additive manufacturing. So this reduces the production resources. The resources I am talking about is labor is also one of the resources only. The labor is also reduced, and the time is also lesser to produce or at least to design something. This is the total advantage model, in which the total advantage for the land, for the labor and for the time that is given in the previous model is given. So land for additive manufacturing for P here means the production, AM means the additive manufacturing processes, T means the traditional methods, U means utilization, and D means the disposal of the product. So land used for the additive manufacturing in production, land used for additive manufacturing in utilization, land used in additive manufacturing for the disposal, minus land used in the traditional manufacturing for production, for the utilization and for the disposal. This is the total advantage in additive manufacturing, that is the additive manufacturing system minus the traditional system. Similarly, for the labor itself, for the additive manufacturing labor for production, additive manufacturing labor for the utilization, additive manufacturing labor for the disposal, if this all accumulated together and subtracted from it is the sum of the labor for traditional manufacturing in production, in utilization and in disposal, this becomes the total advantage for the labor. So total advantage for the transportation, total advantage for the time. In this, the time for additive manufacturing production, time for additive manufacturing utilization, time for additive manufacturing disposal, this minus the time for the traditional manufacturing production, utilization and disposal. In this case, if the time is lesser, obviously the time for T, this would be higher. So here T could be or is higher than T AM. That means this relationship would be negative value. Total advantage for the utilization or utility of the product, so UPAM. UPAM, the utility of the product manufactured using additive manufacturing processes, including the utility gained from increased abilities, enhancement and useful life. Then U for PT, that is for the traditional processes, is again for the abilities, enhancement and useful life. For the traditional processes is again the abilities, enhancement and useful life for traditional processes. This total advantage for the utilities would be utilities for additive manufacturing minus utilities for the traditional system. This is also one of the models given. Additive manufacturing and firm capabilities. A company needs resources, methods, and competencies to develop products and services. Natural resources, labor and other production commodities are the resources. To generate goods and services, the company needs all these resources. So, the company must be able to translate resources into products and services. Two firms with the same resources and methods may not have equal goods due to quality, due to performance, due to pricing difference. So, this difference is attributable to the firm's capability to create a good and service. So, if I say product capabilities, so we have, maybe here we have the resources, processes and capabilities. Because we are talking about a total advantage, the firm or the company which is taking the additive manufacturing has to have good capabilities, and these capabilities in itself should be controllable. I would say controllability of these things, then controllability, then integration and flexibility, which means the firm's controllability. If the firm's ability to control the processes, it means its goal is cost effectiveness, precision and productivity. So, controllability is the firm's ability to control its processes. Its goal is to have cost effectiveness, precision and productivity. So, flexibility of the firms is to handle the internal and external uncertainty. So, if I say maybe flexibility here, then the controllability here. So, the integration as and when the systems keep on going, for this if you say flexibility, if it is reduced, control is better. If the flexibility is higher, control is lesser. But for the longer run, we have to keep on going for higher flexibility, higher control. This has to be a long term goal. This is a long term goal which is practical only using integration. This would be discussed in the last lecture of the course, that is Industry 4.0. How do we integrate everything? How do we connect everything using Internet of Things, using digital manufacturing, using cloud data? How do we integrate so that the flexibility is also there and also we have good controllability? So, flexible firms can handle internal and external uncertainty both. So, that is what is being mentioned here. It involves adjusting to changing situations with minimal time, expense and performance implications. Over time, a company can incorporate technology and information to boost flexibility and controllability. In addition to the entities of capabilities, there are basic process level, system level and performance level capabilities. Process level skills encompass specific functions such as assembling, welding and individual processes. Sometimes the components which are manufactured through additive manufacturing, those do not fit in our build envelope once. Sometimes the components which are manufactured or 3D printed in a 3D printer or additive manufacturing scenario does not fit well into the print envelope. Print envelope, for example, is having only capability of 300 millimeter by 300 millimeter X by Y, but the component size is larger. So, sometimes in the post processing, welding also has to happen, or some assembly using nuts and bolts have to happen. So, these are all individual processes. These are all different process level skills that encompass these. System level skills that translate resources into goods and services. The performance evaluated by profit, revenue or customer satisfaction, it is the final link. To work or to understand the firm capabilities exactly, estimating costing also has to happen properly. For estimating costing, there are certain methods which I will just try to explain now. So, there are certain estimating methods: expert opinion, analogy methods and formula based methods. In the formula based methods, it could be a factor based method, material cost method, function method, cost size relationship. So, to estimate the cost of the product, it is important to have the reliable cost estimates which are necessary for all the products, all the projects that we are taking into account. So, without a proper estimate, it would be impossible to prepare a budget plan or to prepare a business plan and to predict resources, etc. So, expert opinion methods, sometimes the experts, those who have an experience in additive manufacturing, could let us know, okay, this specific kind of the component would take this amount of time, this amount of material, this support would come, they can just let us know this would be the time. However, softwares these days are well enough, which takes the parametric methods. So, expert opinion is a non-parametric method, I would say here. So, these two are the non-parametric, expert and these two. Non-parametric means this does not take any formulas. Formula based methods means the parametric methods. So, backup and historical data are scarce or non-existent, leaving only expert opinions sometimes as the basis for the cost estimate. So, in the expert judgment, expertise should be considered from individuals or groups with specialized knowledge, or they have training already and the team and the physical resources that they have. It is sometimes also guided by the historical information, which provides the valuable insight, that is the secondary data they have also sometimes help them. So, estimates based on expert opinion have a number of drawbacks, including bias, inability to be verified or quantified, but still it is used because we do not have any other option sometimes, and we trust the people who have good experience in this. Potential failure to account for growing program complexity and a general lack of information gathering that can be used to support future estimates. Despite these drawbacks, expert judgment is valuable not only when data are lacking, but also a method of validation for other conceptual estimating techniques. So, firstly, an expert opinion might be taken, then we can also go for the data analysis, collect the data. So, then comes the analogy methods. Analogy estimating, which includes or uses incremental or marginal cost estimating. This derives the price of a new product from information on previous prices or comparable products. So, this is analogous estimating method, in which the scope, cost, budget, duration or measures of scale such as size, weight, complexity is all taken from the previous similar projects. So, when estimating cost using these techniques, it relies upon the actual cost of the previous projects, which is taken from the secondary data. So, it is reliable and little more dependable than the general expert opinion method. Based upon the differences between the new and the old systems, cost adjustments may be made. These adjustments frequently take form of mathematical expressions and may be regarded as formula based methods sometimes. Analogy estimating may be restricted to products produced by the specific facility and calls for analogous products. The estimates often depend upon the static technology. So, if the technology at the facility changes, the analogy estimating relationship would need to be adjusted to take those changes into account. Second, analogy estimates frequently leave out crucial information which drives cost significantly higher than initial cost estimates. Now comes the formula based methods. Number one is factor method, then we have material method, function method, cost size relationships. The factor method is among the simplest, but if the data are kept up to date, it can frequently produce estimates that are fairly reliable. The factor method may use a specific reference or relative basis. So, these are small estimates that we generally use. For example, in an activity, if 400 hours is taken in printing for a specific product, so then we can say that a printer with 2 nozzle heads would take 200 hours, something like that. This is a factor based method. So, I would say 400 hours of a product produced divided by 2 nozzles or nozzle heads gives us 200 hours per piece. If we increase the number of nozzles from 1 to 2. Next is the material cost method. Since the material cost is frequently the second largest cost item, after the machine cost, if it is all distributed along the life cycle, sometimes the material cost becomes the first largest or the largest cost item of the prime cost of additive manufacturing systems. So, in one reported instance, the material cost represented 64% of the total prime cost. The material cost method has been somewhat justified that whatever the material is proportional to that, let us calculate the cost of the build. The function method is comparable to the factor method, but uses more variables and frequently uses non-linear expressions. The function essentially consists of a mathematical expression with constants and variables that estimates the cost for the specified variable levels. So, that means we are trying to put some variables. For example, there could be some method known as 3-point estimating method is also one of the calculation method in which 3 points are taken. One is the most likely, number 2 is the optimistic, number is the most pessimistic. Distribution of the cost, distribution of the time, accordingly it is taken. So, function method is almost equivalent to the data analysis method. In the data analysis technique, the processes include the alternative analysis as well, the ABC analysis. So, all these systems are taken into consideration. There are many different expressions which can be taken here. So, through the unit size, conceptual costing can also be determined. This method allows for either a relative or an actual cost comparison of the cost of various designs. Expressions have emerged based on information for machined parts and investment castings as well. So, these are the major applications of the function method. In additive manufacturing also the similar applications are taken. The cost capacity relationship is followed by a relationship indicating that as a piece of equipment gets bigger or the plant's capacity rises. So, with this the second part of the costing in metal additive manufacturing is completed. I have taken 1 or 2 examples here. Try to please calculate the break even point for the first example, and for the example 2 try to please calculate the selling price and also try to again plot the break even point for those, considering some fixed cost for the equipment there as well. I will meet in the third part of the costing lecture series, in which a new model, that is the total cost model, would be seen, and we will try to see that with help of an example. Thank you.